Hey, what's up, chem peeps? In this vid, we are going to interpret acid-base titration data. Two things we're going to do. One, we're going to calculate the pH through an acid-base titration for both strong and weak-strong combinations. Two, we're going to describe the relative concentrations of the species involved in a titration at various stages of the titration. Alright, so in this video, I'm going to walk you through how to calculate the pH throughout a titration. First, for a strong acid, strong base titration. And then I'm going to walk you through how to calculate the pH for a weak acid, strong base titration. So let's start with the strong acid, strong base titration. We're going to titrate 25 milliliters of a 0.100 molar HCl solution with 0.100 molar sodium hydroxide. Now, for the purposes of this video and to practice calculating the pH along the titration curve, we're starting with a known volume and known concentration of both our acid and our base. So the first thing we're going to do is calculate the volume of that sodium hydroxide required to reach the equivalence point. So let's first take a look at the reaction between hydrochloric acid and sodium hydroxide to form water and sodium chloride. The ratio between hydrochloric acid and sodium hydroxide is 1:1. So if we know that we have 25 milliliters of a 0.1 molar hydrochloric acid solution, we know that we're starting with 0.00250 moles of hydrochloric acid. And because the ratio between hydrochloric acid and sodium hydroxide is 1:1, given by our balanced chemical equation, we know that we need to add 0.00250 moles of sodium hydroxide to reach the equivalence point, to react all of the acid. And because we're working with a 0.1 molar sodium hydroxide solution, and we need 0.00250 moles of that sodium hydroxide, using our molarity equation, we can determine that we need 0.0250 liters of sodium hydroxide, or 25 mils of sodium hydroxide. Now that makes sense because our concentration of our acid and our base are each 0.1 molar, and the ratio between our acid and our base is 1:1. Alright, so let's keep that information in the back of our mind as we work through the steps to determine the pH throughout our titration. Okay, so let's first determine what the initial pH is of our hydrochloric acid solution before we add any base. It's really important to recognize that HCl is a strong acid, so we assume 100% ionization. Therefore, whatever the initial concentration of our hydrochloric acid solution will be the concentration of our hydronium ion. And if the formula for calculating pH is equal to the negative log of hydronium ion concentration, all we have to do is plug in the value of our hydronium ion concentration, 0.10, to determine the pH, which is going to be 1.00. So, as we begin to plot our titration curve, our initial plot is going to begin at pH of 1 before we've added any sodium hydroxide. Alright, next let's talk about how to calculate the pH after adding 5 mils of sodium hydroxide. Let's recognize that 5 mils of sodium hydroxide is coming from our 0.1 molar solution, which means that we've added 0.000500 moles of sodium hydroxide. And recognize that that is going to react in a 1:1 ratio with the HCl, which means that we're going to consume 0.000500 moles of HCl. Recall that we started with 0.00250 moles of HCl, and we're going to subtract the 0.00500 moles that reacted with the sodium hydroxide, which means that we have 0.00200 moles HCl remaining. So to determine the pH at this point, to determine the concentration of the hydronium ion, we've got 0.0020 moles of hydronium ion remaining. Initially we had 25 milliliters, but we've added 5 milliliters of base, so the total volume is 30 mils. If we divide that 0.00200 moles by 30 mils, we get a concentration of hydronium ion to be 0.0667 molar. Again, our formula for pH is the negative log of the hydronium ion concentration, and our new concentration of hydronium at this point is 0.667. When we take the negative log of that value, our pH is going to end up 1.18. So we've become slightly more basic because we've added some sodium hydroxide, neutralized some of our hydronium ion, so there's less hydronium ion in solution. So as we go back to our titration curve, the second point after adding 5 mils of sodium hydroxide, slightly more basic. For adding 10 mils, 15 mils, 20 mils of sodium hydroxide, the process is going to be the same. Be cautious because your volumes are additive when you determine the concentration of the hydronium ion. All right, so now let's talk about how to calculate the pH at the equivalence point after we've added 25 mils of sodium hydroxide. At the equivalence point, recognize that the strong base has completely neutralized all the hydronium ion. It's neutralized all of the hydronium from the strong acid. It's neutralized all of the HCl. And so at this point, the only source of hydronium ion is coming from the self-ionization of water, because the salt that forms is a neutral salt. Therefore, at the equivalence point, the hydronium ion concentration is 1 times 10 to the minus 7. And if we plug that value into our formula for pH, we'll determine the pH of our solution at the equivalence point to be 7. Back to our titration curve. Recognize that at the equivalence point for strong acid, strong base titrations, our pH is going to be 7. All right, so what happens after the equivalence point? How do we calculate the pH after we've added 30 mils of sodium hydroxide, or we've gone 5 mils past the equivalence point? Let's think about the total number of moles of sodium hydroxide that we've added. In this case, after adding 30 mils, we'll have 0.00300 moles of sodium hydroxide that we've added. Recognize that 0.002500 moles of that went to neutralize the original HCl solution, the original hydronium from the HCl, and so we have 0.00050 moles of hydroxide in excess. So let's determine what the concentration of that hydroxide ion is. We know we have 0.000500 moles of it, but again, keep in mind the volumes here. We initially had 25 mils of our acid. We've added 30 mils of base. So the total volume now is 55 mils, which means our concentration is going to end up 0.00909 molar. We can then plug that into the formula for pOH to determine the pOH value, which when we do that, we get a value of 2.04. Then recall the relationship between pH and pOH to determine what the value of the pH will be after we've added 30 mils of sodium hydroxide, which in this case is going to be 11.96. So after the equivalence point, you're basically determining the pH of a strong base solution, because the only thing in solution that's really contributing to the pH are those hydroxide ions, those excess hydroxide ions. And then as you continue to add more and more base, recognize that you're continuing to add more and more hydroxide in excess. The process is going to be the same. Just be cautious with those volumes. Remember that it's additive. Okay, now we're going to work through a titration of a weak acid and a strong base, and we're going to set it up side by side with the calculations that we did in a titration of a strong acid with a strong base. So in our example, in the weak acid strong base titration, it's going to be 25 mils of our acid, but this time it's going to be a weak acid, formic acid. Still titrating with that strong base, sodium hydroxide. Concentrations of both our weak acid and strong base are 0.1 molar. Again, first thing we're going to do is determine how much base is required to reach the equivalence point. Okay, so first thing I'm going to do is I'm going to calculate how many moles of my weak acid I have. I've got 25 mils, it's a 0.1 molar solution, so I have 0.00250 moles of weak acid. The relationship between my weak acid and strong base is a 1-to-1 relationship, and so I'm going to need 0.00250 moles of sodium hydroxide to neutralize my 0.00250 moles of weak acid. Which means that if I'm working with a 0.1 molar solution of sodium hydroxide, I'm going to need 25 mils of sodium hydroxide to neutralize 25 mils of 0.1 molar formic acid. So recognize something very important here. We need the same volume of sodium hydroxide in each titration, because in each titration, we're reacting the same number of moles of acid. Okay, let's determine our initial pH before we add any base for our weak acid solution. Because it's a weak acid, we're going to need to use an ice table. So recognize our initial concentration of our formic acid is 0.1, virtually no hydronium or formate ion. Our change is going to be represented stoichiometrically, so minus x, plus x, and plus x. And then at equilibrium, our concentrations are going to be 0.100 minus x, x, and x. In order to determine the pH, we need to know what X is equal to, what the hydronium ion concentration is. It's not going to be 0.1 molar because this is a weak acid. So we're going to turn to our Ka expression. We're given the value for the Ka of formic acid to be 1.8 times 10 to the minus 4. We're going to make the X is small approximation because our initial concentration, the value of Ka, differed by a factor of 1,000 or more, which simplifies our Ka expression to 1.8 times 10 to the minus 4 equals X squared over 0.1. And when we solve for X, we get 4.24 times 10 to the minus 3 molar. That is our hydronium ion concentration. Now that we know the hydronium ion concentration, we just plug it into the formula for pH. And when you solve for pH, we get a value of 2.37. So important thing to recognize here, strong acid versus weak acid. Same concentration, same volume. The initial pH of our weak acid is higher than the initial pH of our strong acid because remember, a weak acid does not completely ionize. We're not going to have as much hydronium ion in solution. So as you look at your titration curve side by side, your pH of your weak acid strong base titration is going to start initially slightly higher. Okay, now let's calculate the pH after adding 5 mils of sodium hydroxide. Recognize that if we have 5 mils of sodium hydroxide and it's a 0.1 molar solution, we will have added 0.000500 moles of sodium hydroxide. And recognize that the ratio between sodium hydroxide and our weak acid is 1 to 1. Therefore, we will have consumed 0.000500 moles of our weak acid. And because we initially started with 0.00250 moles of our weak acid, if we consume 0.000500 moles of it, we're going to have 0.0020 moles of it remaining. Now, important difference here. Even though we only have 0.0020 moles of our weak acid remaining, recognize in your equation the 1-to-1 relationship between your weak acid and conjugate base. By using up 0.00050 moles of our weak acid, we're going to form 0.00050 moles of our conjugate base. So now in solution, we have considerable amounts of weak acid and conjugate base, which means buffers time. Oh yes, you knew it was coming. Recognize if we want to determine the hydronium ion concentration in a buffer system, we need to think about the concentration of our weak acid and conjugate base. Now notice I'm using the number of moles here because the volumes will essentially cancel out. You could calculate the concentrations, but that's just an extra step. So when you plug this into the calculator, you get a hydronium ion concentration 7.2 times 10 to the minus 4. And when you plug that into your formula for pH, we end up with a pH after the addition of 5 mils of sodium hydroxide of 3.14. So once you start adding that strong base to your weak acid, you are forming some of your conjugate base. And anytime you have weak acid conjugate base, it's a buffer calculation. All right, side-by-side comparison, we do have a slight increase in our pH after the addition of 5 mils of sodium hydroxide. And then as you continue to add strong base, the calculations are going to be the same. However, note that in the weak acid strong base titration, we've got an extra point here. We've got the half equivalence point plotted out. 12.5 mils. Now, the reason why this is important is it can help us identify the Ka of our weak acid if we had not been provided with it, because it's at the half equivalence point that you have equal amounts of weak acid and conjugate base. So the pH at that point is going to equal the pKa. And if you measure the pH to be 3.74, you can then determine the Ka of your acid by doing 10 to the negative of your pH. Note, our Ka, 1.8 times 10 to the minus 4, is the same as the Ka that we were provided with originally. So an important point in those weak, strong titrations is to look for the half equivalence point to help identify the Ka of your acid. All right, let's take a look at the equivalence point for our weak acid strong base titration after we added 25 mils of sodium hydroxide. Recognize that at this point, we have used 0.00250 moles sodium hydroxide. And because the relationship between sodium hydroxide and our weak acid is 1 to 1, we've consumed 0.00250 moles of our weak acid. In other words, we've completely used it all up. But recognize that we've also formed 0.00250 moles of our conjugate base formate ion. And that 0.0025 moles of formate ion is now in 50 mils of solution. So our concentration of formate ion is 0.0500 molar. Now remember, this is all happening in aqueous solution, so all that formate ion can react with water to reform our weak acid and hydroxide ion. In other words, the anion of our salt, the formate ion, will hydrolyze water to form additional hydroxide. So how do we determine the concentration of the hydroxide ion? Ice table. Initial concentration 0.0500 molar. Our change is going to be done stoichiometrically. At equilibrium then, our concentrations are going to be 0.0500 molar minus X, X, and X. All right, let's scoot this up a little bit. We're going to use the Kw expression that relates Ka and Kb to determine what the value of Kb is, because our formate ion is acting as a weak base. So we need the value of Kb. We're given the value of Ka for the formic acid originally in the problem. Next, let's write our Kb expression, plug in the value for Kb that we just solved for, and our equilibrium concentrations. Make the X's small approximation, and then solve for X. When we do that, we get a value of X to be 1.7 times 10 to the minus 6 molar. Remember though, this is our hydroxide ion concentration. So we're first going to solve for the pOH of the solution. When we do that, we get a pOH value of 5.77, and then use the relationship between pH and pOH to determine what the pH of our solution is at the equivalence point. In this case, the pH is going to be slightly basic, 8.23, which we would expect because this is the titration of a weak acid with a strong base, meaning that we're making a basic salt, sodium formate. It's going to hydrolyze water, form additional hydroxide. So very careful here, note that at your equivalence point for a weak acid strong base, the pH is slightly higher than pH 7. Okay, now we're past the equivalence point. We've added 30 mils of sodium hydroxide. In other words, we have added 0.00300 moles sodium hydroxide. Recognize that now our sodium hydroxide is in excess by a value of 0.00050 moles. We've used up all of our weak acid. The concentration of our hydroxide ion is 0.00909 molar. Again, be cautious, your volumes are additive, which means that the first thing we're going to do is solve for the pOH of this solution. And if you do that by plugging in the concentration of our hydroxide ion, we get a pOH value that is equal to 2.04. If you want then the pH, again, recognize the relationship between pH and pOH, which is given to you on your screen, in your notes, and on your formula chart, and you can then determine the pH of the solution to be 11.96. So at this point, recognize the only thing that's in solution that's contributing to the pH of our solution is that excess hydroxide ion. It's just a pH of a strong base calculation. So note, our plots are going to start to line up, and that's going to continue as we continue to add strong base, because in both titrations, in both examples, the solution is now just excess hydroxide ion. That's the only thing contributing to the pH. All right, I highly encourage you to take some time, go back, review, compare, think about what you have in solution at the different points along your titration and how to calculate the pH at those different points. We are done.